great pleasure to be here today with Professor Mingxun Wang. Professor Wang is at UC Riverside at the Computer Science and Engineering Department. So his education was in UC San Diego, where he did studies with Nuno Bandeira, who's doing a massive thing on proteomics and running large-scale grants there, and also at UC San Diego. And then he did a postdoc at Peter Dorrestein's lab, who's a very well-known person in metabolomics, mass spectrometry. So that's a really tight collaboration between Nuno Bandeira, Mingxun Wang, and Peter Dorrestein for a long time. So since 2017, so at least 2010, if you think about
go back.
So it's like going back 14 years now, which made really best use cases for the UC San Diego Supercomputing Center and all the resources there. So that was really helping a lot the field, as you will see. But also now he's an assistant professor. Before, however, he was an undergrad at University of Illinois from 2009 to 10. And even there, he did GPUs, right? So he did stuff on GPUs, but I felt like, okay, that was early. Yeah. They came onto fame later, right? So Professor Wang has an age index of 40 and I-10 of 70. But he is rising very, very fast. He's a rising star. He had this year 7,700 citations, which is more than I have. So woo! So meet famous Dr. Wang. The floor is yours.
Well, thank you for the kind invitation and introduction. I try to be more of a modest, so don't read too much into that. No. It's low expectations. And throughout this talk, feel free if you have questions, during, after, for clarifications. One of the big advantages of coming here is to meet all of you and to have a conversation. So we wanted to be very loose. But again, thank you for the invitation, Oliver and Arpana and all the organization from Jeanette. It's been a wonderful experience so far. So just to give you a little background, I started my position at UC Riverside just a little over 2 years ago. So we're a brand new, still getting started lab. And we'll talk to you about some of the work that I've done at UCSD, as well as kind of the pathway and new projects that we've done at UC Riverside as well. So that'll be kind of what's covered here. So here are my disclosures. And I want to start off here as kind of a very central analytical chemistry question that we've been thinking about the last decade or so. And so we have some sort of biological, environmental sample that we want to analyze and ask a question about. And what we can do to ask what are the particular metabolites, small molecules that are present in there is something, a technology we're all familiar with, is using mass spectrometry to get out the structures that are actually present. Now, if it were only so simple, right, that our mass spectrometer directly would actually give us the 2D molecule structures. Again, this audience is very familiar with. That's not what it does, right? And we happen to live in this world where the mass spectrometer, when we use tandem mass spec approaches, we end up with tens of thousands, or depending on the instrument, hundreds of thousands of tandem mass spec for all the analytes within that particular sample, right? That's the situation that we're in. And this can be thought of in some sense as an intermediate representation of data that we're looking at. And then ultimately, we want to be able to turn this data of the tandem mass spec back into the structures so that we can start reasoning about chemistry, biochemistry, and ultimately perhaps the biology of the system that we're talking about. So this is one perspective of kind of the problems that we want to solve. How do we get from here to there? And so to just give us an understanding and a kind of a scaffold of where the progress we made over the last 10 years. So this is a little bit older. We published this paper back in 2023. But this is a rough understanding of how we could actually identify relatively confidently all of the public tandem mass spectra from metabolomic studies throughout the years. And so back in 2014, we stretched this back, it was less than 1% of the tandem mass spec we could actually identify. And I think this less than 1% is a kind of an injustice. It was far less than 1%. And so throughout the years, we've steadily been able to start increasing these identification rates. And so thinking about what constitutes being finished, but at least we can start measuring progress as a community throughout the years. And I'll talk about some of the approaches that we've used to help drive this. And of course, we're not the only group doing work in this area, so definitely don't want to discount the rest of the community. But here's just one perspective on some of the computational innovations that we think have moved the needle over the years. And so number one, just to have this ball of everything that we can at least access with tandem mass spectrometry, there's 5 to 15% of compounds that we know and we can re-identify of this big pool. And so that's kind of be the very first pillar that we'll talk about. And the second is, how can we start expanding this domain of knowledge that we've curated and understood, so that we can start slowly expanding this into new molecules that have not been discovered, but it's related to these things that are known. And finally, approaches to start tackling and mining for new pockets of chemical novelty that exist in all this public data, or any sort of untargeted metabolomic study that data is being generated. So broadly, kind of the outline of this particular talk, how do we identify knowns? And we'll talk a little bit about the crowdsourcing that we did a while ago, propagating from known to unknown, and how do we think about expanding this knowledge. And then also finally a language to think about mining all of this data to generate some new discoveries that may not perhaps be related to known compounds that are in these knowledge bases. And so one of the things that I just want to outline here, kind of a common approach to identifying compounds that we've already known within untargeted metabolomics data sets, is this idea of spectral library search. And so perhaps I may have a tandem mass spectra that is generated in my particular sample. I don't know what it is, right? As it comes out of the mass spectrometer, I don't know what it is at that time. And I can ask the question, have I seen this tandem mass spectra before, right? So if I have, and then you can think about also wrapping other sorts of analytical measurements, retention time, and ion mobility as other parameters. But if you could ask that question, have I seen this particular tandem mass spectrum before in a library where I knew the structure? If you can answer that confidently, yes, then I can take that structure that was in the library that I've remembered previously, and be able to say, okay, this new metabolite, or this metabolite that I'm observing in my particular sample, I've seen it before, I think it's this particular structure, right? Pretty straightforward, just ask this kind of similarity question. Now, there's various ways that we can measure similarity, but very abstractly, if we think it's similar, then we can just compare it to the library and get the structure that way. Now, the real question that comes at this point is, where the hell do I get the libraries from, right? This is kind of the key bottleneck. Comparing to nothing, if your libraries don't exist, this particular approach doesn't help you very much. And so one of the things that we did, or were inspired by back 2013, 2014, is this idea of leveraging the broader community. And we knew that we couldn't generate all the standards and all the libraries and solve all the structures in the world. And one of the areas that we originally targeted and that I was a part of was not particularly metabolomics, but it was natural product discovery. And so this is a field where people, when they solve structures, these novel natural products that are very complicated, it may take months to years to solve these things. You need to grow up bacteria, you need to purify, you need to solve the NMR. So it's an extremely laborious task. And so you couldn't even buy these standards. And so that's kind of where we were coming from. And so we borrowed these ideas from other resources that were around us. One of them was PDB and the other one was Wikipedia. And so these successfully leveraged the community to start building up this database of knowledge. And so over the last 10 years, we built up such a resource in GMPS, or at least part of GMPS, where we asked the community to contribute tandem mass spectra and their structures and deposit into a place such that it was immediately browsable by the community, usable by the community, and could be leveraged in computational algorithms immediately after deposition. And so back then, we started with a few thousand compounds, and it slowly grew throughout the years. And through the efforts of the rest of the community as well as GMPS community, we've aggregated a lot of these resources. And today, it's actually this is a little bit dated, but it's in the hundreds of thousands to peaking at over 1 million, I think, of experimental tandem mass spectra that's publicly available for search by the community. And so some of the other resources that we've imported to just kind of aggregate this all together, so a lot of the key sources were MassBank, Mona, and some from Bruker, some collaborations with Bruker. And so that's all kind of piled in here and made available for the community to use. And so one of the questions that we had back in 2014, 2015, when we were building such a resource, we asked, well, how reliable could such a community resource be, right? These are the original criticisms of Wikipedia. And so one of the things that we did to start measuring this effect is we took everything in the GMPS libraries. We did a library search against all the public raw metabolomics data that was deposited at the time, a few thousand data sets. And those were our putative identifications, right? But again, we want to measure how confident is the library plus the ability of this library to actually identify known compounds. And so we asked the depositors of these data sets to go back and say, yes or no, are these correct? Because they would know their data set the best in the biological context and things like that. And so we asked them to rate it from 1 star being incorrect all the way up to 4 stars being correct. And we wanted to understand, was the crowdsourced resource as accurate as other gold standard resources at the time? And so when we did this, we compared to things like NIST and MassBank. So predominantly, we want to take a focus on NIST here just because it's from the Department of Commerce and the National Institute of Standards and Technology. This is going to be very well curated and kind of the gold standard in terms of quality. And what we found was, these are two different subsections of the GMPS libraries, but we found that they were at least as good in terms of these 4-star correct rankings for identifying compounds as NIST was. So that gave us confidence that at least in these early stages back in 2016, the GMPS libraries weren't so big. It was somewhere around 100,000, I believe. But they were giving us quality as assessed by manual curation of people who deposit their data as being as confident as NIST. So that gave us some confidence that we're not doing such a bad job, or the community's not doing such a bad job in providing spectral libraries as a starting point to build up this knowledge. And so that effort, and as the libraries grew from a few thousand to hundreds of thousands and over 1 million, we were able to measure that it steadily increased the identification rate of all this public data. So that's great, right? So we're going from something that's way less than 1% to a few, 4 or 5%. Now, if we want to get to being finished with this particular problem, it's great that we made such good progress, but this is not particularly a great path forward to get to 100% or some semblance of being done, right? This rate of a decade of progress and getting to 4%, it's a Herculean effort, but it's really not that scalable. I don't want to wait another 50 years, right? And so one of the other things that we started doing is asking, could we take this knowledge that we have, these MSMS spectral libraries, and instead of identifying simply the known compounds again and again, can we start thinking about expanding that knowledge from known to unknown with little steps? And so that'll take us with this little step function here at the very end. And so again, I think there's been a lot of work from this group as well. So and maybe I'm preaching to the choir here, but one of the key things that we took a look at back in the day was asking the question of, and developing this intuition. Imagine there are two very similar structures that are not the same, right? So here we see that the main core of this particular antibiotic is very, very similar, but the tail length extends a little bit. And so if we ask the question, if we put both of these molecules into the mass spectrometer, do the tandem fragmentation, what does the MSMS spectrum look like on the other side? How are they different? How are they the same, right? The intuition here is that they should be very similar just because generally we would expect the same sort of fragmentation mechanisms, but it won't be exactly the same, right? And so this is the actual tandem aspect that comes out, but we'll talk about the intuition in just a second. But broadly, the shape of the peaks is very, very similar, but some of the masses differ a little bit. And so at least analyzing the intuition and our hypothesis of the mechanism that we can think about and to develop the computational algorithms that will try to take advantage of this phenomenon, we can have two molecules here on the top and the bottom. And my apologies to the chemists here. This is definitely a computer science drawing with this little delta group here. But what we have is two molecules, very, very similar, but it differs by this addition of a delta. And so what we can imagine that happens is if we have the same fragmentation point highlighted here in the dashed blue line, on the top molecule, we end up with a purple piece and an orange piece that manifest themselves in the tandem mass spectrum. Similarly, in the bottom spectrum here, if we imagine the same bond breaking, we end up with a blue piece and the orange piece. And the orange piece will occur at the same mass because it's exactly the same as the top molecule. Now the blue piece here will occur at a mass that's shifted, right? Because it has that delta. And the shift is exactly that mass of this delta. And so what we can start thinking about is we can consider peaks when we align the peaks from the top molecule and the bottom molecule in the tandem mass spectrometry space. They can either be at the same mass, as we see in the orange, or we can also consider each peak being shifted. We just don't know a priori which ones will shift and which ones will not. We don't know the structures, and we can't predict very well the fragmentation, even if we did. And so we have to consider that entire alignment space. And so we specifically here, we can assign contributions if this particular peak was at the same mass or shifted, and the alignment can only be that each peak is either at the same mass or shifted. It can't be both, right? And then so we can explore this particular space, we can explore this particular alignment, and kind of from computer science terms, we formulate it as a bipartite matching problem and solve it with the Hungarian algorithm. So this is a very classic approach in algorithms and computer science. And so this gives us a framework to think about how to tackle this particular shifting peak phenomenon when the structure subtly changes just a little bit. Now, one of the things that arises with this sort of formulation of the problem is it works really well or reasonably well whenever there's a single structural modification. But a problem may arise when there are two structural modifications, as we see in the right-hand side. There's a delta and a gamma. And the problem is, whenever we measure both of these molecules, we can't tell what delta and gamma are. We know what delta plus gamma is, but we don't know how to separate the two. And so this particular formulation is not particularly great at capturing multiple modifications that are happening here. Okay, so fortunately, a lot of the samples that we were looking at, especially bacteria at the time, biology seemed to offer a solution for us, that multiple of these modifications don't happen all at once, right? And what we'll expect to see is there may be some intermediate product which has one of the modifications, and then another final product that has both of the modifications. So this intermediate molecule will allow us to bridge this double modifications with a single modification here in the middle. Okay, so that's that's kind of one of the ideas that we had. And so we wanted to think about scaling this idea up to all of the tandem mass spec within one particular experiment, right? So we can start really arranging and asking what are the pockets of molecules that we think are putatively structurally similar even before we've done any identification. Now, so this is the concept that underlies this molecular networking approach, but I want to talk about some of the computational challenges and innovations that are necessary to make it practical. Right? And so if we take this idea kind of at first glance, if we scale this up, we do pairwise similarity, even if we start defining some very high similarity thresholds, what you end up with something like this, where each circle here in this particular figure represents a unique tandem mass spectrum, and connections represent a high spectral similarity between the MS-MS spectra with this alignment. This is not particularly explorable by the average chemist that actually wants to make some sort of discovery. So, we just call this, hairball networks, not the most fun thing to explore. What we eventually want to start doing is we want to start doing some filtering into distinct families with a nice layout that allows chemists to actually start understanding, exploring the diversity that's actually present. So this is called our filtration step from this hairball into something that's a little bit more understandable as a practical approach. So the very first thing is human interpretability. But number two is, even though we have this formulation of a spectral similarity, there's going to be false positives. And the filtration steps helps reduce the false positive connections in the molecular networks. And so one of the things that we didn't do when we introduced this molecular networking 10 years ago was we actually start measuring how good are the networks that come out of here. And so one of the things we wanted to actually start measuring now is what is a good network and what is a better network, right? So if we start thinking about computational innovations, we need to be able to actually measure any sort of progress we want to make. And so one thing that we want to start talking about is how accurate is the network. When we start filtering the network, the particular subcomponents that come out, are they correct? Are we getting consistent structural grouping there? And to counterbalance this, we want to ask, how complete is the network? Do we put more than just, we don't want to separate out the network such that it's just a bunch of single molecules. The whole point is to have network connections to have some sort of clustering. So we want, at the end of the day, as big of networks as possible, balanced against as accurate of networks as possible. So there's these two metrics that we want to think about. And so the very first one, about accuracy, we can just simply, once we create these networks, we can look at the 2D structures and we can ask about structural similarity. How close, if we can use things like Tanimoto similarity within these networks to actually start measuring. Now, if we want to think about completeness, we can...
Can I ask a question?
Yeah.
So go back.
Yeah.
Okay, so when you look at this little partial network thing, and you have a similarity 0.9, is this Tanimoto?
This is going to be visual. Yeah, Tanimoto here. Yeah.
So, but when I look at these two structures, as a chemist or as a biochemist, they are not related at all.
Okay. So we need metrics. Maybe Tanimoto is not a good one. Another separate thing, and I don't talk about it in this work, but we throw on things like classifier and look at the consistency of the classification within a particular component. The point is taken. The idea here is that we want to measure structural similarity. Now, how we can do that, you can take a multitude of approaches. We started with both of those two approaches because they were the simplest for us to kind of explain and kind of explore. But then there's other things, maybe from a biochemistry perspective, maximum common substructure or edit distance or something like that may be more appropriate depending on the kind of application.
Well, because it started with the application, I say, I have a structure A, I put delta on, and then I put gamma on. So that's that's a biochemical perspective.
Right, exactly. That's a good point. That's a good point.
And now we are at a very abstract, high level.
Right.
Motor thing.
Yeah, exactly. So that's a good point, and that's something actually we probably should revisit in the context of this work. That's a very good point. That's a very, very good point. So that correctness aside, so we can definitely do a lot of different things. But another thing that we want to measure is how complete are these networks, right? We want to have a single metric that can easily describe how complete these molecular networks are. And we borrow some ideas from the genomics side where there's this idea of the completeness number, or many of you may be familiar with these N50 when we do genome assemblies. And so similarly, what we want to do in the molecular networking side is we can ask if we want to cover 50% of all the unique molecules in the network, what is the smallest component size that comes out? So I'll show you in a quick example here. So this particular network here on the left has bigger families. Right? You can see these little groupings, there's more nodes, and there's actually more connections. Here on this right-hand side, there's less. They're almost singletons, maybe they're doublets. And now what we want to do is we actually don't do 50%, but we do 20%. We count from the biggest to the smallest components. We stop once we've captured 20% of the data. And then we can ask, how big is that last component? So in one single number, again, it's not perfect, but in one single number, we can start capturing this idea of how big are the components between these two results of filtration. So, and then once we have both of these methods about accuracy and completeness, we want to start asking the question, where are we today? Right? So on the GMPS side, we have, I will tell you, the particular, well, first, there's the baseline where we don't do anything, what happens there. And then there is this classic GMPS heuristic method that is described in the literature and described in the papers, but I will tell you, it was Christmas break 2013, and I just made up what I wanted to do, and it was just very arbitrary. So we never explored this over the last 10 years, and people have been suffering with the molecular networks that I created, these decisions over that period of time. So it's just very interesting for those of you that are grad students. You never know some of the choices you make, how it ends up. So it's just as a short other anecdote, I will tell you this. The output files on the GMPS side for the molecular networks, there's some tables, and there was a column for the network pairs, I believe, and there's a lot of stuff to do, and I was like, okay, I need to write this column out. I'm going to reuse it for some other purpose, and I just named the column in this tabular file MEH, because meh. I was right. I was in a hurry, right? I was debug. It's not really critical. It's just kind of a debugging thing. I've seen people on our forums trying to figure out what that acronym meant. So it's just small. Anyway, so here we have this visualization of the existing methods. So I just want to explain this. Here on the x-axis is completeness number, right? How big are the networks? And here on the y-axis is accuracy. So where we want to live is in the top right corner. We want to be, again, as big of networks as possible, as accurate as possible, right? Again, there's going to be, at the end of the day, we're not going to be able to end up there, but there's going to be a fundamental trade-off of the bigger the network is, the less accurate it will be, right? And so we can see here in this, I think, brown here is this baseline. So we're sitting somewhere along this baseline if you don't do any filtering. And the classic approach, we did some, this hyperparameter kind of search to understand where is that distribution for the classic heuristic approach. And so we see it's around blue, and the star, this is the default within the GMPS ecosystem. So it's not that we're doing nothing. We are improving, but we think there's significant space to improve beyond this. So as computer scientists, the most natural thing about filtering, instead of all this heuristic stuff, we want to be elegant about it. We want to look for cliques in the network. Right? So just to give you an idea for those of you who don't understand cliques, if we have this as our raw idea, we want to find subnetworks that we can say, they're all connected to each other. The fragmentation is very consistent. We want to look for those kinds of things. Again, it's a very natural thing for us as computer scientists to formulate as a computational problem and see how it works. Now, when we do that, we show here in the green triangles finding cliques. So we actually do pseudo-clique finding to make it a little faster. But at the end of the day, what we find is that, yeah, it's really good at making really accurate networks when they're really small, right? And so it doesn't scale. It's the accuracy starts falling off as you get bigger and bigger. And it's good if you really want these tight, accurate, small networks. But it doesn't really improve across this big gamut range of completeness. We want to move the whole curve to the upper right. And so we take some ideas from proteomics. So this is some work that my advisor had done and Nuno had done a long, long time ago in looking at post-translational modifications of peptides. And so the key point here is that they were able to do a multi-spectrum alignment of MSMS spectra of peptides with different PTMs and visualize it in this sort of way. And so what we thought about is, why can't we do the same thing? And one of the weaknesses, or the reason that we came about to this particular idea is that the clique finding fails because we have situations where a spectrum A here and spectrum B here have two modifications. They will never appear in a clique because when you align A and B, it's not going to work. If we use the original formulation of the problem, it kind of harkens back to that same problem where it's biting us again. However, if we have this molecule C in the middle that has that one structural modification, what it can do is bridge the alignment between A and C. And so what we can think about, we call this transitive alignments. Instead of trying to align A and B directly, we align A to C, C to B, and use C as a bridge to realign the peaks. And we can reuse the same formulation. And so just to give us an example here, there's three structures that are outlined here that are several modifications apart between molecule X and Z. If we just do the naive alignment that we talked about, we have a few peaks that align. Great. That's not terrible, but a few peaks align. But if we use Y here at the very top as our bridge to go through them, we can see the entire spectrum starts to align. So that's the way that we can reevaluate alignments during the construction time using these intermediate spectra as transitives.
So the similarity is not a real cosine, so it's some kind of modified cosine.
Right, so exactly. So it's a modified cosine in the original formulation where you can have a single modification. But then whenever there's kind of two steps, right? Which peaks align, and then you score those alignment.
So what's the exact mathematics here?
So you would say you align X to Y, and then Y to Z, and then what you can do at the end of the day is, because this peak aligned to this peak, you can say this peak aligns here.
Oh, okay. You just transformed, or you just take it carry forward.
Yes, yeah, exactly.
Carry forward.
Exactly. You can carry it forward, but the way we actually approach this algorithmically, it's not limited to a single intermediary. What you actually have is this network, and you can do all these different paths to find the optimal alignment path. So we kind of skipped over that, but that makes it a little bit more interesting and a little more computationally expensive. But that's the fundamental, the premise here. And so just to give us a little example where this is the original network that we came out, if we look for cliques, we would end up with cliques A and B. However, we want to make the networks as big as possible, and we know that these are structurally similar. What we can do is the transitive alignments will insert these dashed edges because we can transitively align and bridge the alignments with these middle MSMS spectra. And then at the end of the day, if we do clique finding again, it'll capture everything into one particular family. And so where does that get us? So what we can see here in red is it starts giving us these sets of red squares, and it moves us a little bit further to the top right. Now, this is an exploration of where we are, and it improves things, especially in the smaller regime, but does significantly better than the cast algorithm. But one of the other things that we wanted to explore is that what is the theoretical maximum that we could achieve if we had the perfect network. And so that's what we highlight here in purple when we have the true structural annotations and we leverage this back. If we had, again, we can calculate this upper bound. So there's still a gap. There's still room to improve.
How did you simulate this upper bound?
So we know the structures on the MSMS spectra. We throw away the MSMS spectra.
Okay, so you take the annotations.
Exactly. And you simulate the ideal network that can maximize this without even thinking about the MSMS spectra.
But the annotations you have might be wrong.
Well, that could be wrong. It could be wrong. So these we took from libraries.
Okay.
So these would be standards that were run. So in the grand scheme of things, this is probably the lowest level of error that we could get out of this. So this is not specifically on real data that we did MSMS annotations on. This is actual libraries. Okay, so that's one key step to make the molecular networks interpretable. And so I just want to show one particular application to motivate this next question. So one of the things that we did back in 2020 was we were able to identify within some germ-free mouse study. So the biology's whatever, but I'm sure it's important. Don't get too flip. But so what mattered here in this particular story is that there was a particular family of molecules. Again, each of the circles represents a unique tandem mass spectrum, and the connections is we think they're structurally similar. And this was prioritized based on some sort of expression pattern between the germ-free mice and the pathogen-specific mice. And so what we could identify was this particular 466M/Z molecule, and this happened to be a cholic acid conjugated with glycine. So this was known. This is produced by the host. But everything else in this network was unidentified, so that was kind of an opportunity. And they were, especially down here, they would be produced by the microbiome or metabolized by the microbiome. And Emily Gentry and Robbie Quinn, actually I forgot to put his picture up here, but what they were able to do is because they are chemists, they know mass spectrometry and they know some biochemistry, they were able to take this tandem mass spectrum, look at the difference and say, okay, we think this is cholic acid over here, this 5,6, that's been, where the glycine is substituted with a phenylalanine. So they did a lot of work. They manually curated this and putatively identified new molecule. Now, they did the same thing down here with cholic acid conjugated with tyrosine. So they were able to do this manually looking at the spectra and propagating from known to unknown. At very minimum, we've moved the needle with molecular networking because we've told them where to focus their efforts. So that's great. But I'm fundamentally like a lazy person. I don't want people to do any work. And so we asked the question, okay, what is the sort of insight that the chemists were using to actually think about what's going on to propagate this annotation to these annotations? So one of the tools that we came here, or we recently introduced, is trying to actually define this as a computational problem and seeing how well we can actually solve it so we can take it out of the hands to some extent or make it a little easier for chemists to repeat this particular operation. And so what we have here, just as an illustration, so this is some cover art, is we have a tandem mass spectrum on top of a molecule that we know. And on bottom, we have a tandem mass spectra that we don't know, but it's putatively an analog because the similarity is very similar or very high whenever we do the alignments. But what we also can notice is that there are peaks that are shifting. And if we can use these peaks in an interesting way, we may be able to focus and understand where that structural modification occurred on the known molecule. And so we want to define this as the modification site localization problem. There exists some ambiguity where that particular modification can occur. So let's try to predict that actual occurrence computationally. So ultimately, this problem setup again is that we have a known MSMS spectrum with a known structure, and we have a putative analog MSMS molecule, and we don't know the structure. But we think that it's that modification can occur at multiple sites, and we want to be able to say at the end of the day which specific atom would that modification actually occur on. And so again, the intuition here is very straightforward. It's that if there's a peak that moves, we think, and shifts by exactly the mass of the modification, we hypothesize whatever substructure that peak represents, that is where the modification occurs. If it doesn't move, there can be multiple reasons why it doesn't move, but at least in our formulation, we hypothesize it does not include where that modification actually occurs. And so if we can use that information, we can start thinking about prioritizing which particular atom the modification actually occurred on. And so the method that we go through is this. So first, given our known structure and our known tandem mass spectra, we want to start explaining this fragmentation. So we happen to use some of the combinatorial in silico fragmenters, and we get hypotheses as to what does each peak represent in the original structure. Now it's not perfect. It gives us a lot of ambiguity, and some peaks don't have any annotations, any substructure annotations. But this is our starting point. Number two is we actually do the alignment between the two spectra of the known and the unknown. So that will reveal to us which peaks shift and which peaks do not. And number three is depending on which peaks shifted and the substructures they represent, we increase this likelihood that that's the site of a particular modification. And if it does not shift, it decreases the likelihood. And so we hope that there are multiple peaks that shift with complementary information such that the intersection will give us the most likely location of the modification. And so we ask the question too, how well does this actually work? And so what we can see here is there's several different methods on the bottom side, but what our baseline are these randoms, right? So we can randomly predict the site, and on the y-axis here is our evaluation score. How well does our site localization actually work? And so this evaluation score, I won't give you the particular math, but the intuition behind it is that we don't predict a particular site, but we predict a distribution across all of the atoms in a particular molecule. And one of the things...
Did it again with libraries?
Yes, all of libraries.
So these are annotated libraries.
Annotated libraries. And we look for pairs of structures that differ by one single edit. Okay. And so, yeah.
And you used all available mass spectra, QTOF, and Orbitrat?
So what we did was we only did it within a library that would be consistent instrument and fragmentation. Okay. And so we would do it, at least in the SI, it's across several different libraries. And so yeah, I think we did it across QTOF and Orbitrap. And there's actually a follow-up paper we just submitted. The data is not included here, with Agilent, with multiple collision energies, multiple adducts, and things like that.
And RC is what?
So these are two different random predictions. So just to give you an idea, again, the way we evaluate this is we predict a distribution. The ideal distribution is it tells you it's a single atom, and it says every other atom is not applicable, and it's correct. That's ideal. What's not ideal is you get it wrong, or you say every atom is possible. Both are not helpful, right? So this kind of balances that you are pretty focal in your prediction, and your prediction is correct. So that'll give you a 1.0. And so these different randoms, one is predicting exactly a random single atom being correct, as well as predicting all atoms as being correct. So those are two random things that we can do. And then this ModiFinder, MFN, that's our baseline naive implementation. Just to give you an idea, it outperforms the random here, right? So the numbers are higher. Right? So you can see that in the distribution. Now, there is additionally an MFR in orange here, and we can see that it goes higher still. And so the innovation here is the refinement of the substructure annotations using multiple spectra to collaboratively filter the explanations as well as predictions of the formula of the MSMSPs. So that brings us a little bit higher. And finally, what we also try to measure is the optimal performance on this data as an estimate of the upper bound of performance, so that's in green here. And just as an explanation, here is the way we achieve this is we reveal the actual localization site, and we filter the substructural explanations such that it must be it must include the modification site. So the ambiguity is still there a little bit, but it must be the correct one.
So why don't you use deep learning here?
We first introduce the problem,
Okay.
and it's a good suggestion.
Okay. All right.
So my strategy in kind of some of these problems is we want to first understand the problem and formally define it and have the right data and have a baseline. And then we can start thinking about, what are better ways? Just because these are the most obvious ways of implementing this particular solution algorithmically. We know it's going to be somewhat robust just because this training data aspect is not in play. But we do think there's significant advancement here that is possible. Okay, and the final thing, and what we also revealed here, at least from the algorithmic perspective, is that one of the key drivers, and again, not particularly groundbreaking, is that you need shifted peaks in order to achieve localization performance. If your peaks don't shift, at least in this particular formulation of the problem, the algorithm fails. And so we can see here in red, if you have no shifted peaks, the average performance score is not good. Once you start having more and more shifted peaks, the performance increases. But other things that we want to just bring attention to is that the other drivers of performance are substructure annotation ambiguity. So if there's a huge amount of ambiguity in the explanation of the MSMS2 peaks, and it basically covers the entire molecule, that peak is not helpful. And also, if you have no fragments, it's kind of related to the shifted idea, you also have no information. Yeah?
With ModiFinder, how much increase of the annotation rate you can increase?
Right. That's a good question. That's a good question. So one of the things that we did here in this kind of next slide is that we wanted to ask that particular question. For the things we can identify, what are some confident neighbors we could start thinking about propagating to? So this just gives us a taste of this. We haven't kind of really finalized this particular work, but this gives us a taste of it. And so this is some work with Wang, and he's actually this has actually been published, so you need to update this slide, but he's now at the University of Antwerp as a new faculty member. And so what we did was we created these networks, and we did library search to identify known pockets of molecules. And then we asked the question, confident propagations. We see multiple of these deltas occur across multiple data sets, so we know it's real alignments, or we hope that it's real alignments. And so if we started from about 1 billion spectra and we just created the networks, we looked at the neighbors, we get about 88,000 putative unique neighbors. Right? So we cluster these things, and what if we take this as a library, as a proxy for a library of what we can actually start annotating, this gives us a pretty big boost. So it goes from this 4 or 5% up to this 13%. Again, it's not going to be the same level of annotation that you would get from a pure standard that it matches exactly, right? So it would say, it is putatively related to this known molecule with this sort of site localization, and it doesn't give you the full structure. But it's at least, this is the space that we're talking about of how much it could actually provide. Does that make sense?
Yeah. And down the road, when a client or user have this result, how is that computational recognized, indexed, like being understandable comparing one study to another? How do you represent this analog?
Oh, okay. So in terms of representing the analog, so the identifications will happen separately, right, with library search or however you want to do it. Now, whenever, for these things, these propagated spectra, they're available as you can use them to search. I believe it should have the instrument type, collision energy, if it was available. So those are all available. But if you have within your own data set, and so this is how we've implemented on ModiFinder on our side, is if you create a molecular network, then what you can do is all the putative neighbors, because it's a propagation from your own spectra to a related spectrum, it just happens to be identified externally by a library, it can just do it automatically within 2 spectra within your own data set. Does that make sense?
How would you name it?
Oh, how do you name it? Okay, we don't name it. We don't name it. So we provide, right now on the ModiFinder side, we give you a probability distribution. So I'll actually, okay, I don't have that slide active. But we give you a probability distribution of the likely sites, and we allow we are not super confident yet to be able to narrow it down to a single atom in most cases. So it's kicked back to the user to kind of say, it's this versus this based on sort of chemistry knowledge. So the way we do it here is it's actually pretty devoid of chemistry knowledge. So there could be significant improvements if there are some sort of tools out there with some sort of chemistry or fragmentation inspired rules that could further filter these things. Yeah.
So I think, so first it's a very good approach, but I think in terms of the prediction of the modification side, the result will highly depend on the spectral prediction, right?
Yeah.
The process for generating in silico spectra.
Right.
And so right now you are using your own algorithm, or?
So the in silico tool, that is just basically a re-implementation of Magma/Medfrag, those combinatorial fragmenters. So in at least, I totally agree. Like how you do it, how you refine it, and it could be better. It can affect it, right, in the performance. And we thought that would be the most sensitive way to capture the substructures. And in some cases, the least biased, but maybe it's the cost of performance. But I do agree that there can be significant improvements. And we saw it here too, right? We applied Sirius on the MSMS spectra to explain the formulas, and that was used to filter some of the structures out, as well as using other MSMS spectra in the libraries, and we look at consistency and things like that to further refine it, and it does enhance performance. But there's definitely a lot of play here, as well as there's a lot of peaks that are shifting. I don't know the exact number, but there's a lot of peaks that are shifting that have no explanations, even with the combinatorial fragmentation. So we suspect we're not doing any fancy rearrangements to try to explain anything. So there's a lot of open, advancement that could be captured in that direction. Yeah.
You increase the identification rate to like more than 10%.
Right. This is if you included these propagated, that's the space. It's thinking about one shell neighbors, confident one shell neighbors past the identified compound.
Yeah, but have you estimated the accuracy of those 10%?
Right. So that's something like very carefully going back and figuring out the structure. So that's something we have not actually paired this specific pool specifically with ModiFinder and kind of kick it back to the community and say, okay, how accurate is this, and just really solving that structure. So that's still open. That's kind of an open question. So that's a good point. Yeah.
Going back to what you said for Shen's question, have you considered including like information from Mass Frontier, because that's like literature based?
Oh yeah, from the thermo side.
Yeah, the thermo side.
We
that library would be very useful.
Right. So I will tell you some of the things that's a good idea. We have not. So the areas, we're data, so the areas that we're working on is, well, let's collect MS3 information, right? So once we have that, maybe that's another driver for explaining the fragmentation and constraining the fragmentation explanation at the MS2 level. So that's kind of a direction that we're pushing forward on. But that's a good. I'm just not super familiar with that curated area. So if that's something you all are interested in, let us know. So you might be better equipped, especially with like MS Finder and things like that, than we are. So.
Have you thought about using UVPD or adding UVPD and EAD spectra?
Yes, yes. So that I emailed somebody in your lab, but I forgot to follow up. EAD spectra specifically. So we have some examples of this where it's a lipidomics application just because they were collecting it. We just don't have very much, and it's much richer, and we do see some shifting in it. And in the examples that we found, it does significantly help. So that can be an avenue forward. What we did explore, and this paper is under review right now, is positive and negative mode and different adducts. And what we found there was, and all this is all CID on an Agilent instrument, and different collision energies, is once you throw all of that, at least within that particular space together, we found that it can turn bad into good. So there's some, like, say, positive mode, it just doesn't fragment. The negative, makes up for that. But when the positive and the negative and different adducts fragment well, it does not turn good into great. So there's a finite limit on the amount of complementarity in that particular space. And so that's what led us to try some of these approaches on EAD spectra. And it seems like it's a path forward. We just don't have quite as much data, so we're trying to work on that. But if you all have that, I've seen sometimes.
It should be in Mona, right? Yeah.
Okay, I looked at the time. Maybe this was a few months ago. So.
Not easy to download.
Oh, that's
It
fine.
is on Mono, but it's not easy to download. So we usually just go directly to Fangio and ask for it first.
Maybe that was the situation that we ran into. But this is definitely a path forward. So if we can generate more fragments and better explanations, these are definitely the two prongs that would probably have the biggest bang for this particular computational problem. Yeah. So are we, it's 11 o'clock right now.
Don't worry about it.
Okay.
No, I mean, we told everybody it's going until 11:30, so that's what we told people.
Okay. No, I thank you for the question. No, it's more fun this way. So that's one of the finishing that chapter. That's some of the work that my labs are working on of defining this particular computational problem. And this other thing, another tool that we just got it accepted in principle a few weeks ago is we created a language to be able to mine data. And so I think for some of you in the audience that are more computationally minded, you're like, whatever. But I'll motivate this to you all from the chemistry side, some of my collaborators, and my own laziness as well. So again, the goal here is we want to start thinking about these pockets that may exist in the data that we can start pulling out and prioritizing for exploration and discovery that is just a little more difficult right now, especially for chemists. And so the motivating question is, through the latter years of my postdoc with Peter, we're good friends. I'm a computer scientist and he's a chemist, so it's a fun relationship. And we have all this data out there, right? And especially in difference from about 10 years ago, sharing has become more of a norm within the field. And so he kind of asked this question: hey, we've got all this data. We can do the libraries, sure, but can we think about casting a slightly bigger net and asking the question, find me all putative carnitines, at least as a working set for us to think about as a community across all of the metabolomics data. And so I know a little bit about mass spectrometry and chemistry and fragmentation and things like that. And so I know, okay, I'm trying to interpret this question. There are certain types of compositions, certain types of substructures that may yield unique patterns in the mass spectrometry, whether MS1, MS2, or retention time and things like that. Right? And so for carnitines, I can interpret, well, okay, there's the quaternary mean head, portion of it, and maybe there's like a 59 Dalton neutral loss from the precursor and things like that. And so I can obviously go and write a custom piece of software to accomplish this particular task. And I'm sure other people have done similar things, right? But the problem, and we can do this, we can scale it up, we can run it on our particular system. But the problem is, the moment Peter realizes, or a lot of chemists realize they can do this, they will come back to me. There's a saying in English, I don't know if you're familiar with it. If you give a mouse a cookie, he'll want a glass of milk, right? So They always want more. They were like, well, what if I could do all these brominated compounds, these siderophores? Oh, the list goes on and on. And I'll tell you from my own laziness and my own interest, I'm not doing that. I'm not doing that for them. And so, but what's more interesting is just thinking about, because there's some sort of solution that we can create such that I don't have to do anything, but they can get all the power that they want. So we think maybe it seems to be reasonably working today. And the solution that we came up with is a new language called the mass spec query language, so MassQL for short. And we want it to be, these are the kind of the design pillars. We want it to be understandable for chemists if they're going to read and write this particular query language as opposed to writing Python, C++ code. It should be easy. It should be very, very easy. It should be flexible. It should be able to describe all the things that they actually want to find in mass spectrometry data. Right? Maybe a tall order here, but at least this is our first effort at trying that. And we want it to be reasonably scalable. We want to have people search more and more data. It's not particularly useful if you can search 5 spectra or even 1 LCMS run. You probably could do that manually. But we want to get into the regime such that you could not possibly think about, you would drive yourself crazy. And we also want this to be reusable and reproducible. Right? So you spend all this effort doing something. You want to be able to convey that to others in a very succinct manner. And they can take what you did, reproduce it, and change a little bit without reading a couple hundred lines of whatever code that you actually wrote. And so just to give you a little highlight of what make each of these sections. First, about understandability and flexibility. Again, this is a subset of what we can do. So, but we just don't want to overwhelm here. But number one, for all of you, this is very obvious, right? We can look for masses. There's a mass I want to look for, right? I can look for losses from precursor if it's an MS2 spectrum. We can look at gaps between any set of peaks in the MS1 or MS2. And you can look at relative peak intensities, right? Very straightforward. Now, the power really comes, you have the customizability for each of these primitives, as well as combining these primitives together with conjunctions, right? You can say, I want to find this mass in MS1 with a particular isotopic pattern, and the MS2 must have this, with this sort of retention time, this sort of mobility, and you can just push that out there in a succinct expression. Right? Now, these are some examples of the language, but maybe you don't know it. I promise it's actually easy once you get through your first couple queries, but I'm also pretty lazy. So one of the things is, since we start working on MassQL, LLMs have become more of a popular thing. And so these days, you can just talk with a chatbot. It'll write a MassQL query for you, and you go about your day. But so I just want to share one particular anecdote with a collaborator, Daniel Petrus at UC Riverside. So he's a natural product chemist, biochemist, and does a lot of mass spectrometry. And so this is some work that he had published back in 2017 is when he was a postdoc in Germany. And he was looking for a class of natural products called albicidins. And he happens to know that this family produces unique fragmentation in 460 and 660 M over Z. Again, very, very straightforward, but it's just a very simple illustrative example. So he could write this particular query very, very, very easily. And so what we were able to do was go back to his data and apply MassQL and recapitulate the structures that he found back in 2017. Right? So he found them, and you're like, okay, obviously it's these kinds of things. But now when we start casting a bigger net with MassQL, what is striking for him, at least, was that he was able to capture all more putative albicidin molecules that he did not find in his own data, because he was not exhaustive and his analysis was not complete. And so we can see here is the molecular network. In blue are what he had published on, and in gray is what MassQL had fished out, and we could put this together into a particular molecular network. And so this combination of being able to quickly define what you want to look for, apply it and integrate it downstream with other tools, and be exhaustive about what you're searching for, it made rediscovery and discovering new things possible. Right? So that's just kind of one anecdote. And then number 3 here is the scalability aspect. And so one of the things that we recently were fortunate to get this published was some work that Ipsita had done in looking for new bile acids. So I talked a little bit previous in this talk about some new bile acids were discovered. They were manually propagating through the molecular network. But the hypothesis that Ipsita had was, well, can we start capturing all these variants of these particular classes of bile acids across all data and cataloging all this? And so she knows a little bit about bile acid fragmentation. I have no idea. And so she was able to write, again, a very simple query. The actual ones are a bit more complex than this, but this is kind of her illustration here. She was able to write this particular query, and she was able to throw it against all of the Q-exactive data that was in the public domain across 3 repositories. And so it was about 100 million tandem mass spectra, and that filtered down to about 270,000 MSMS spectra. So she was able to do it. She does not need to talk to me about that particular work. And then we do some post-processing of clustering and deduplication and grouping it up by similar structure or putative structures with molecular networking. But the net result of all this, when the publication was, we started with 97 known bile acid modifications. But because she cast this big net with peaks that were specific for these mono, di, trihydroxyl bile acids, without caring about these conjugations in the tail, they were able to find a few thousand more modifications of these bile acids that had MSMS evidence. And so that was kind of the net results. And they talked about there's more diversity and it has a bigger role in mammals, some biology. But the broad conclusion here, from my side, computationally at least, is that this enabled Ipsita, who is a brilliant scientist and chemist and biochemist, but not a computational person. She was able to do this by herself without involving me to run something for her across a large swath of data. And then she can take the query, modify it, and she did, and share it with others in the wider community as a reproducibility aspect. And in terms of reproducibility, one of the things that we wanted to emphasize is it's not just a thing that you can run a GMPS or GMPS2 over at UC Riverside. We want people to speak the same language with the same sort of expectations that's integrated in multiple pieces of software. And to that end, we have these Python and R APIs for MassQL, as well as integration within a lot of common open source software that's popularly used. And so if you write a particular query in one platform, you can put in a paper, give it to a friend, they can run it in their other platform. And so we have things like OpenMS, MSDial, MZMind supporting it, as well as very recently at this last ASMS, Metaboscape from Bruker builds it directly in. And so they're particularly excited about the IO mobility portions of it. But we hope it becomes something that's easier and easier to use. And so I think at the end of the day, hopefully the answer is yes, maybe exclamation point. But we've been very fortunate, or I've been very fortunate that there's been a few dozen papers using it before our paper. Well, there's the whole thing. I've been a little lazy to get the paper out, but that the community has been supportive to even try out some new crazy ideas that we've had. And so just to recap, we started off thinking about how do we start capturing knowledge to re-identify known compounds across this big set. We moved on to thinking about how we can start expanding a little bit, step by step, from this known to unknown with these alignment, ModiFinder, and molecular networking ideas, as well as MassQL. Maybe that allows us to start exploring new pockets that are not related to things that are known that could be exciting. And so all this could not have been done without great collaborators throughout the world over my academic career. I've been exceedingly fortunate over the last 14 years to work with some great people. A lot of them are at University of California, and as well as my grad students at UC Riverside. They've been fantastic, as well as the funding, but they get their due. So,
all right, thank you so much. Great presentation. With your permission, we'll publish it on YouTube.
Oh yeah, sure,
Okay,
fine.
good.
I don't think it's offensive to anybody. So
No, exactly. That's all good. Are there further questions, please? Yes, push it.
Yeah, so first I just want to say congratulations on the MassQL. I heard that you just published, the manuscript has been accepted, right?
Oh, you just got accepted at Nature Method, so it was,
Oh, okay.
yeah, it was fun. Yeah, it was
I
fun.
read the manuscript during my PhD. So
Okay, cool.
2 years ago.
Yeah, yeah. It's
So yeah, I found it's a very useful tool. So I just have a question on MassQL, which is sometimes we don't know the rule, and we just know the functional group, right?
Right.
So how can we approach this question?
right. Okay, so that's a good question. So there are several things that we've done in some other works that I'm going to reference. So there's a tool that came out in 2015 called MS2LDA. So then there's a follow-on tool called MESAR, but broadly they try to explain different conserved fragmentation motifs in the tandem mass spectrum, and MESAR will try to associate it with actual substructures. So that may be a decent place to start where people have annotated these kinds of things. Another thing that we try to do, it's with middling success. I'm not sure if it's the right approach, but it's leveraging the MSMS libraries. Just search for the substructure you want. It'll find all the MSMS spectra that occur. And this is more of a manual approach, right? And then it looks at the conserved fragmentation. So you can do this on the GMPF2 side, but we just haven't published. It's just it's something to try out. I just haven't spent the time to figure out like how do we measure and really think about that very accurately. So.
Do you think that like the tools like Canopus can help this problem?
It's in the forward direction, right? You want to really push it in the opposite direction.
Yeah. So basically, the question is, if I want to find a certain substructure, and see if the substructure to find all the features or spectra contains this substructure.
Right.
And but I don't know the rule, right? Because sometimes their substructure, maybe there's a cleavage in the middle of the substructure.
Right. If the fragmentation changes, especially in the context, in the structure context, maybe not Canopus because that's the classification, but you could try simply getting the CSI finger ID predictions out, right? And if you can figure out the meaning of each fingerprint dimension, right? And then you could search based on that, right? That's another approach that you could do. But the underlying assumption on the MassQL side, it's MassQL, not structure QL, right? But it would rely on a conserved pattern, so it may not be able to cast that bigger net. But if you transform it into structure space and you rely on the fingerprint being correct or accurate, maybe that's a decent way to do it.
John?
Yeah. So I have a question. There's a certain class of molecules that I work with a lot that do have good rules for fragmentation, but it's dependent on positional placement. So basically, dihydroxides and epoxides and aliphatic chains cleave in a specific way, but the fragment you get will be dependent on the overall structure.
Okay.
Aliphatic chains, where double bonds are, what the size of the fragment is, but that cleavage is very characteristic. So, have you tried to think about that kind of aspect, that essentially you need the total molecular weight, you need the total mass, as well as the rule, and the fragments in the context of the total mass to tell you the presence of
I see.
oxide is there, the diol is there.
I see. I think you can actually maybe do this just because we introduced this concept of variables, like masses can be variables, and you can do sort of compositionality against. I'm not sure if you can actually represent the precursor, but if you can represent the precursor and have it as it's almost like it's like a linear equation almost, right? Where you want to have that precursor equal the mass plus, to some sort of addition or subtraction. It might not be exactly there, but let's talk about it.
Yeah,
Let me talk about it.
at lunch.
Yeah.
Anyone else? Yeah? Fanjo?
I really like your idea of the transitory search, let's call it. But I was wondering, so you mentioned there needs to be a middle spectra that bridges the spectra A to B, right?
Right.
Does the middle spectra have to be existent in the database in the first place, or it can be back-propagated using
I see. Yeah. So there's two ways you could think about simulating it, right?
Yeah.
That's one aspect. You could think about sourcing it from public data.
Yeah.
That's another approach. And then the final thing, kind of getting around this idea of requiring the intermediate, is there are algorithms. So we have just published a couple prior to this. Is actually being able to do a multiple alignment or multiple modification alignment.
Oh, so basically the middle spectrum is just like it's just like imaginary thing. It doesn't have to be exist.
Well, so yeah, you could have, there are alignment schemes. So when we presented this here, the alignment scheme can only work essentially if there's a single modification, at least that's the premise.
Yeah.
But there are alternatives where you don't need that middle element, and you could do it such that it could account for multiple modifications directly.
Yeah.
So the one is, it's called simile. It is extraordinarily slow, so which is one we don't use it. But that's something you could do. That's something you could do.
Yeah, I was thinking maybe, like, for example, if even though if it's like a multi-step modification, you can backpropagate like the middle spectrum every time, and then you match it to the public space.
Oh, you could.
That would give you some more information about the
Right. You could do that. I mean, even easier. You didn't have to even think about synthesizing it, right?
Yeah.
You literally could just say, I mean, you all are familiar with on the flash entropy side, is you could just take your MSMS spectra and just search it against the repository and see if there's a middle bridge. You can do that, right? Just do it directly, right? Without having to imagine what it could be. Just ask, does it exist? And then that would be a solution to that. Yeah.
My question is also about like the error rate. If you do like a 2 steps propagations, the error rate will be like a negative factor.
Right.
So then you can have much more error. How do you have any ideas to control error rate?
Right. So there's 2 aspects to this. From a you don't really want to, right? You basically you don't want to predict out the full structure at the end of the day of 2 steps, right? And I don't even think we really want to predict the full structure right now, given the amount of information in tandem, a lot of tandem aspect for a single step. That's why we say here's the probability distribution of where the modification occurs. Please resolve the ambiguity because it might be 2 atoms. There's an example in a previous talk where it's a small molecule or a natural product. It's quite big, and it's rich fragmentation, but we can't figure out which there's a benzene ring, and we don't know which site on the ring it is, but we know it's on the ring, and we looked at the correct one, and it's on the ring, but we just don't have enough information to figure that out. So I think there's a danger in producing an actual SMILE structure and trying to like decorate that and pushing it forward. Now, another thing we have done is if there's multiple modifications, especially if you have in the intermediate is, in this transitive networking idea, is we can generate 2 probability distributions. So you can imagine no molecule modified with 1, modified with 2, right? We can capture the alignment kind of carefully, and what we can produce is the prediction of the 2 modifications separately, as opposed to together. So then you don't multiply the error. You're like, we think this first modification occurs on this part of the molecule, the second occurs on here. We don't try to resolve them one then the other to accumulate error. We can give you the prediction separately. So it's like a 2-step ModiFinder approach. So that's one way that we've been trying to think about without cascading these errors, if that makes sense.
All right, I have another question. So we are here in the Genome Center.
Yeah.
In the Genome Center, people like about genomes and genetics and proteins and protein folds and all these things. And we also have a host of people who send us data sets, or actually samples and we turn into data sets. So they ask us what to do with the data.
Okay.
And if we don't give them a structure, then they say, I will ignore it. So if we don't give them a SMILES at least, they will say it's an unknown, I don't care.
Okay.
And that's the first thing they throw out. It's absolutely no doubt about it. I understand. I am the first one to acknowledge the danger of false claims, right? To say, oh, I give you a structure, it is at that ring at the 4 position, right? But if you don't give them a structure,
right,
then they will throw it out. And no structure, no name, throw it out, right? So that is a problem here. Have you thought about saying that on the one hand, we might have completely new structures and have unheard of, nobody's ever seen them. On the other hand, we only have MSMS spectra for maybe 100,000 molecules, whereas 110 million molecules are in PubChem. So maybe it could be one of those compounds that are already in PubChem or in natural products. So with all the possibilities of, you know, the modification on the ring ABC, you know, hey, there's a structure which is in PubChem that has this modification.
Right.
And so it might have a higher probability because somebody already deposited there, and so on and so forth. So hey, you know, while I'm not sure, I can give you that thing, so that you can propagate it into genomics, proteomics, you know, biochemistry, nutritional biology, circadian rhythms, whatever, right? So something that you will say like biology, biology, but this is what they care for.
No, I agree.
This is what they actually care for.
No, so first, I very much appreciate that perspective, and that's why for a lot of my collaboration, I love having a chemist in between me and the biologist, right? We all sit together, and they, you know, so number one, I think that's a good idea, especially the prior probability of being correct. You know, we have to ask the question: what is the likelihood, or how much confidence does that prior probability actually bring us, so that we understand quantitatively, are we doing the right thing and actually increasing confidence? But I think there's also this aspect of there are other things that we can give that contain that ambiguity, right? So there's like I forgot what the Markush structures on the Inchy side. So that's recently standards are arising. So we can give them a structure, yes, but it implicitly encodes that ambiguity so that there's nothing lost in translation, right? They don't. You might write an email or a result that says it can be this, but there's some ambiguity, and they just truncate it at the can be ambiguity step, right? So I'm very careful of that, right? So it's not a bad idea. It's not a bad idea.
Great. So are there further questions right now? Otherwise, we'll be happy to see you during the afternoon. Thank you, everyone.
Yeah,
Thanks for joining.